Hey, today's video is essentially a fundamentals of electricity. And so what I want to look at right now is essentially what actually takes place when you decide, hey, I'm in the mood, I'm bored, coronavirus is going around, I think I want to go lick a battery. So what actually takes place when you decide to reach your tongue out of your mouth and actually lick a battery? What's actually taking place? So most of us acknowledge the fact that there is obviously you feel a little tingle in your mouth, maybe a little lightning bolt there. You feel a little tingle in your mouth. What's actually happening between these two poles of the battery? Now, the thing that we usually notice is we have a positive and a negative pole on the battery. And obvious enough, I've downloaded this battery and I don't really remember which side is the positive and which is the negative. But in the end, it's completely irrelevant in how we work these problems. Essentially what happens, we learned in static electricity, you can imagine there being charge on one side, a depletion of charge on the other side. So what happens is this charge of electrons wants to flow from one terminal to another. So literally what you're feeling is this charge, this flow of electrons through your tongue. This flow of electrons, that flow of charge, that's actually what we refer to as current. So that is what current is made out of. And current itself is measured in a unit of amps. So we use capital letter A, but usually we say amps. Specifically, it's actually in terms of what it is, it's a coulomb per second of charge. And you have to remember back to when we first talked about charges, a single electron has a charge of 1.6 times 10 to the negative 19 coulombs. So if you saw a current flow of 1 amp, that means there's 1 coulomb of charge every second flowing through there. And we could grab a calculator very easily and go 1 divided by 1.6 times 10 to the negative 19, and that would actually tell you the number of electrons flowing through there. Now, one of the things you've probably noticed before is this. When you stick the battery to your tongue, you feel a charge, but if you were to just take a finger and reach out, and that is a terrible looking finger. If you were to take your finger and reach out across the terminals of the battery, you're not able to feel a charge when you reach out across there. So hopefully you've got some ideas to the reason why, but it's got to do with your resistance. The resistance of your hands, and resistance just means the ability to not let those electrons flow. And we could go into what makes a resistor and the conductor, but that's not where we're aiming at in this video. But your tongue has a much lower resistance. It's got a much lower resistance. You got to think it primarily because of the moisture involved in there. So you're able to have this flow take place through your tongue. Now, so this idea of resistance is usually what's measured in ohms, and we'll fill a table out in a second. I know that's kind of a odd looking little Greek letter for you there, but it's actually what's known as an ohm. And so that's how we measure resistance. Now, there's one other thing. All right, so most of us would be willing to reach our tongue out and lick a 9-volt battery. But when it comes to a wall outlet, most of us would be very reluctant to reach out, and please do not put your tongue in a wall outlet. That would be a very bad idea. But what is the reason why? How come I can touch my finger to the 9-volt battery and I feel nothing, but if I grab a hold of a wall outlet, I definitely feel the buzz? Well, that's because we've got one additional thing that we've got to take into account. That's the potential. And notice how most people just say it's the voltage. That's not the sexy science word for what we're looking at. What we're actually referring to here is a potential. And so like your wall outlets is actually 120 volts. Now, technically 120 volts AC, but we're not to a point that we want to discuss that right now. But obviously you can tell you've got a much greater potential in the wall outlet. And if you're trying to grasp what this concept of potential means, to me it's kind of like, this is the way I just teach it to get a basic idea. It's kind of like the push, the ability to actually push those electrons through a material. So in the case of the wall outlet, 120 volts has a much higher potential, so it's able to push those electrons through something even like your skin. So let's take a second and do a little summary here. All right, so our three fundamental things that we need to be looking at. Potential, the symbol that we actually use for potential is a capital letter V, and the unit is also V. So it's actually measured in volts. Current, on the other hand, the symbol that we use for current is the letter I, and the unit for current is the amp. And remember, an amp is nothing but a coulomb per second of charge. The thing you got to think about when doing problems with electricity, you got to think of a wire, kind of like a wire is a pipe. So you can imagine these electrons, it's just like water flowing through the wire. These electrons are moving through the wire. So that's where a resistor comes in. A resistor is kind of like an obstruction. It's kind of like a stopped up piece of the pipe, and what's essentially happening is it's harder for these electrons to get through these materials. And so resistance we take into account with the capital letter R, and the unit we actually use then for resistance. And if you keep hearing a rooster crowing in the background, that's Chickaletta. I know Chickaletta is definitely not a boy name, but that's what my son calls the rooster, so he's Chickaletta now. Anyway, and so we actually see the unit. If you're trying to figure out, well, where does this ohm come into? And it's because our fundamental equation is actually what's known as Ohm's law. And I will butcher his name. It's not George, it's Georg Siemens Ohm is actually, I'm pretty sure, the pronunciation. So as we take a look, Ohm's law is very straightforward. Potential is equal to current times resistance. So if we look, we'll see a couple of relationships. Potential and current are directly related to each other. So if you increase the potential, you'll increase the current, which is why you definitely don't like grabbing wall outlets. More potential, more current. Also, if you have a higher resistance, then it takes a higher potential to actually push the electrons through. Now, while those are all direct relationships, current and resistance are inversely related to each other, because you have to think, if you have a greater resistance, then you have less current flowing through that material. So that's where that comes in. So what I want you to look at now is this basic circuit diagram. You're going to see a lot of these. And so first I want you to look at this. This represents your potential in the circuit. And some people would say, well, it represents a battery phi. You can say it represents a battery. I don't care what you call it, but that is your potential. The symbology is the long line, the short line. And so you might have something like a 3-volt potential in a circuit, which a 3-volt potential, that would actually be like 2 AA's, 2 AAA's, 2 C's, 2 D batteries. They've all got the same 1.5 volt potential each. Now this A is actually what's referred to as an ammeter. Now what's funny in the lab is we usually don't talk about ammeters too much anymore. And matter of fact, something that's kind of missing most of the time in pictures, you will see something like this. You will see the same circle with a V in the center, and it'll be drawn around something. And so that's a voltmeter. The reason why we don't talk about voltmeters and ammeters so much in the lab is we have what's kind of like this picture I've got to the right. And usually shorthand, we refer to this as a digital multimeter. And what's cool about this is if you look at the amps written on here, like you've got 3 different units for amps, this device is capable of measuring current. So if you set it up to measure current, you can measure current. You'll notice how I've got ohms on here, so that means that this device is capable of measuring resistance. We've even got capacitance on here, which we're nowhere near there. And then this one is also capable of measuring potential on here as well. So we can use this same device and dial it and we can actually use it to measure anything we want in a circuit that we build. We do have to change how we wire it up. For example, you can see here, these are called ports. It's where the leads of the meters plug in. The common is always the common, so you'll always have a lead plugged in there. But say, for example, if you want to measure volts or ohms, you would plug your other lead into this port, or if you want to measure amps, you would plug in over here. Reason why is these ports are usually fuse protected. What's cool is this: it's almost impossible to blow up a voltmeter, but when you're plugged up into this amps port, the meter is very susceptible, because look at the diagram. If you notice over here at the diagram, I'm going to change my color again. See, the electricity is actually literally going to flow through the ammeter. And so we see the electricity flowing through the ammeter, and that's why if the current reaches too high of a value, it will literally smoke or burn the ammeter. So that's why they have fuses built in. We would say that an ammeter is placed in series in a circuit, because what you're doing is this: you're using this resistor to try and basically defend your ammeter. So they're literally connected in a line to each other. So like this is what a resistor looks like. They're usually small silicon devices, and the color bands on there help tell you what it is. For example, let's look at this one. Here we've got one that's orange. I'm going to call that brown resistor. That orange, brown means 3, and brown means you times it by 10. So that's a 330 ohm resistor. And you may be going, well, what's this little, and it's supposed to be the color gold. The gold just tells you that this resistor is guaranteed to be within 5% of its promised value. Some resistors have silver. Silver just means within 10%. So this resistor should be within 5% of its promised 330. So the deal is, if you want to use this ammeter, you literally need to have one lead of the ammeter connected in a series with this resistor. This resistor will kind of defend your meter. The voltmeter, on the other hand, the voltmeter can be what we call as connected parallel. Voltmeters have a huge resistor. It has an internal. Here, I'll write internal. It has a huge internal resistor which defends the voltmeter, which means when you connect the voltmeter, there will be almost, I'm going to write I equals 0. There will be almost no current flowing through the voltmeter. It's got a huge resistor. And so it's able to tell you the potential across, like in this case, it tell you the potential across this squiggly line, which that is what the resistor is. And so we do all this because we're about to start seeing these problems in these pictures, and what you've got to be able to do is look at the picture and identify what's going on. So like we'll do a video next where we actually solve some Ohm's law problems, which again is V is equal to IR, and they're usually very simple. Something as simple as if you had a 9-volt resistor and a 100 ohm resistor, what is the current in the wire? Well, I think we can handle that math easy enough. 0.09 amps of current would be flowing through the wire. I'm not going to spend a lot of time on V equals IR, because I think if you're watching this video, you're good enough at physics, you can probably do basic electricity problems. But anyway, we'll continue and talk more in other videos.